Alright, let's continue. Let me open the table of content first. Okay. We are on chapter 22, Beyond Physical Memory Policies here. So let me open that. Okay, if I remember correctly, we are on this section using history to LRU, least recently used. And then now let's take a look at the workload example. Okay, where is it? Workload example. Let's look at a few more examples in order to better understand how some of these policies behave. Here, we will examine more complex workload instead of small trace. Okay, more complex workload. Okay, instead of small trace. However, even these workloads are greatly simplified. Alright, even these complex workloads are greatly simplified. Better study would include application traces. Okay. Our first workload has no locality, which means that its reference is to a random page within the set of access pages. Oh, okay. No locality. Alright. In this simple example, the workload access 100 unique pages over time, choosing the next page to refer to at random. Overall, 10,000 pages are accessed. Okay. The workload access 100 unique pages over time. Alright. Choosing next page to refer to at random. Overall, 10,000 pages are accessed. Okay. In the experiment, we vary the cache size from very small, one page cache size, to enough to hold all the unique pages, which is 100 pages, right? This one. We are accessing 100 unique pages over time in order to see how each policy behaves over the range of cache size. Over the range of cache size. Okay. The no locality workload. This is the hit rate. This is the cache size. Okay. Now are you the least recently used, first in, first out, and then random? Okay. That looks similar, I guess. At least in my eyes. There might be a little differentiate here and there, but overall looks the same to me. Yeah. Okay, figure 22.6. the no locality workload. In figure 22.6 plot the result of the experiment for optimal least recently used, or LRU here, random and first in first out, or FIFO here. The y-axis of the figure shows the hit rate that each policy achieves. The y-axis varies the case size as described above. Alright. 100 case size, I guess. Again, all the unique bits, right? Okay. We can draw a number of conclusions from the graph. First, when there is no locality in the workload, it doesn't matter much which or realistic policy you are using. LRU, or least recently used, first in first out, or FIFO, and random all perform the same, with the hit rate exactly determined by the size of the case. Okay. When there is no locality in the workload, it doesn't matter much which realistic policy we are using, right? That's why I don't really see any difference here, or at least significant difference in the graph. Okay. Second, when the case is large enough to fit the entire workload, it also doesn't matter which policy you use. Oh, when the case is large enough to fit the entire workload, it also doesn't matter which policy you use. All policies, even random, converge to 100% hit rate when all the reference block fit in the case. Yeah, when all reference block fit in the case. Finally, you can see that optimal perform noticeably better than the realistic policies. Peeking into the future, if it were possible, does a much better job of replacement. Right. Okay. The next workload we examine is called the 80-20 workload. It exhibits locality. Oh, okay. We use locality now. 80% of the reference are made to 20% of the page. 80% of the reference are made to 20% of the page, the hot page or the active page, I guess. The remaining 20% of the reference are made to the remaining 80% of the page, the cold page, or maybe the inactive page. Maybe in our workload there are a total 100 unique pages again. Those hot pages are referred to most of the time, and cold pages the remainder. Okay. Cold page the remainder. Figure 22.7, page 10 shows how the policies perform with this workload. As you can see from the figure, We'll put random and first in first out to reasonably well. The least recently used does better, as it is more likely to hold onto the hot page. I'm assuming the active page, maybe something like that. But yeah, I'm not sure what this means. Refer to most of the time. Okay. Is that mean the hot page is the page that active most of the time? Maybe. And the cold page here the reminder that the page that not active most of the time. Maybe. Okay, as it is more likely to hold onto the hot page, as those pages have been referred to frequently in the past, they are likely to be referred to again in the near future. Again, the second workload having locality now. So we are considering the frequency too. I think it was called not spatial but temporal locality. This one, temporal locality, which said that pages that have been accessed in the near past, or maybe recently, I guess, are likely to be accessed again in the near future. Okay, the temporal locality. Again, as those pages have been referred to frequently in the past, they are likely to be referred to again in the near future. Optimal once again does better, showing that least recently used historical information is not perfect. Right. But it does perform better though than the first in first out and random, I guess. I mean, for the random part here, yeah, it depends on the luck, you know. It is random after all, right? You might now be wondering, is LRU or the least recently used improvement over random and first in first out really that big of a deal? The answer, as usual, is it depends, right? It always depends. What is it called? It really have any hard answer? Is that the hard or maybe specific answer? Yeah, it usually depends on the circumstance or something like that. Its miss is very costly, not uncommon, right? Okay, wait. If its miss is very costly, not uncommon, then even a small increase in hit rate, reduction in miss rate can make a huge difference on performance. If miss are not so costly, then of course the benefit possible with least recently use are not nearly as important. Then even the small increase in hit rate, the reduction in miss rate, can make a huge difference on performance. If myths are not so costly, then of course the benefit possible with discretionary use are not nearly as important. Right? It depends. Okay. Let's look at one final workload. We call this one the looping sequential. Oh, one final workload. I mean, we haven't looked at the... Where is it? Oh, this one, okay. Yeah, I missed that. We haven't taken a look at the figure 22.7, right? So let me take a look at this first. Okay, the 80-20 workload. This is LRU. Okay. Alright. Yeah, this is kind of interesting that in this graph at first, right, there's not much difference between the LRU, FIFO and random, right? But then as we fill out the case, the LRU, what is it called? The LRU perform significantly better, I guess. And yeah, it's kind of interesting that FIFO and random didn't have any significant difference. Okay, maybe we are lucky enough that the random here perform almost the same as the first in first out, or maybe unlucky, I guess, because sometimes the FIFO policy, what is it called? The FIFO policy can perform worse, you could say, like when we, what is it called? When we want to access the next page, right? But it turns out that page have been moved out from the memory beforehand. So we will hit miss, right? So yeah, it's kind of interesting in this graph. The first in, first out and random didn't have significant difference. Okay. Let's look at one final workload. Ooh. It's called. Let's look at one final workload. We call this one the looping sequential workload. Oh, looping sequential. Okay, as in it, we refer to 50 pages in sequence, starting at 0 and then 1 up to 49, up to page 49. Okay, we refer to 50 pages in sequence. Alright, and then we loop. Oh, repeating those access for a total of 10,000 access to 50 unique pages. So instead of 100 unique pages, like the two previous example, now we only have 50 unique pages, but we are doing a looping here. We iterate the, what is it called? This 50 pages in sequence, right? And then what about the case size? Do we still have 100 case size? The last graph in figure 22.8 shows the behavior of the policies under this workload. Yeah, there's no information about the case size. I mean, I guess it can be different, the performance, depending on the case size. I mean, on previous session we take a look at the Pilates anomaly here. The first in, first out might get worse depending on the sequence, right? If the case size increase. And well, the random is also susceptible to anomalous behavior. Okay, something like that. So yeah, I'm kind of curious what the case size is. Maybe we will find that out when looking at the figure 22.8. Okay, this workload common in many applications. Oh, common in many applications, okay. Including important commercial applications such as database. Oh, okay. Represents a worst case for both least recently used and first in, first out. These algorithms under a looping sequential workload kick out older plates. Oh, okay. Unfortunately, due to the looping nature of the workload, these older paths are going to be accessed sooner than the paths that the policies prefer to keep in cache. Okay. These older paths are going to be accessed sooner than the paths that the policies prefer to keep in cache. Again, we are we iterate in sequence, right? So we are starting from 0 again. I assume something like that. Okay. Indeed, even with a cache size of 49, oh, looks like the cache size is 49, I guess. A looping sequential workload of 50 paths result in a 0% hit rate. Oh, okay. Interestingly, random fares notably better, not quite approaching optimal, but at least achieving a non-zero hit rate. Oh, interesting. We have a 0% hit rate for the least recently used and first in, first out policy, and then non-zero hit rate for random. Well, maybe we are just lucky, you know. That's why we have a non-zero hit rate. Turns out that random has some nice properties. One such property is not having weird corner case behavior. Oh, okay. Oh, alright. I guess we are only taking a look until cache size 49, but the maximum is still 100, I guess. Okay. perform better. Oh, wait, where is the LRU in this graph? I didn't see the LRU here. Wait, hold on a minute. This yellow line is the optimal, right? And then this blue line is the random. And then this green X is the first in, first out. But where is the circle blue? Circle like blue. Yeah, this one. The circle like blue. I don't see that. Does that mean the LRU is not in this figure? We are not even considering LRU here. Is that it? I mean, the first in first out is there, even though it is 0% hit rate. Oh, wait a minute. Okay. Yeah, I guess I can see the light blue here. Okay, it is being covered by the green X here. Okay, alright then. Implementing historical algorithm. As you can see, an algorithm such as least recently used can generally do a better job than simpler policies like first in, first out or random, which may throw out important bits. Okay, implementing historical algorithm. As you can see, an algorithm such as least recently used can generally do a better job than simpler policy like first in, first out or random, which may throw out important bits. Unfortunately, historical policies present us with a new challenge. How do we implement them? Right. Let's take, for example, least recently used. To implement it perfectly, we need to do a lot of work. Specifically, upon each page access, that is, each memory access, whether an instruction fetch or a load or store, we must update some data structure to move this page to the front of the list. See, we must update some data structure to move this page to the front of the list. Contrast this to first in, first out, where the first in, first out list of page is only accessed when the page is fixed. By removing the first in page or when a new page is added to the list, right? So in the first in, first out list of page, we are only accessing the list when we are removing the page or adding the page to the last inside. To keep track of which page have been least and most recently used, the system has to do some accounting work on every memory reference. Right? We need to keep track of the memory usage, I guess. The recency of the memory. Clearly, without great care, such accounting could greatly reduce performance. Right. One method that could help speed this up is to add a little bit of hardware support. We are adding more hardware, I guess. Instead, one method that could help speed this up is to add a little bit of hardware support. For example, a machine could update on its page access a time field in memory. Okay, for example, a machine could update on its page access a time field in memory. For example, this could be in the per process page table or just in some spared array in memory. With one entry per physical page of the system. Okay. A time field memory could be in the per process page table or just in some spared array in memory. Right. I guess, one of the possibility is to put the time field, the recency time field in the page table entry. I guess. I assume from this explanation, right? In the per process page table, we can add the time field in the page table entry or in a spared array in memory. Is this array per process though? Or maybe share? I'm not sure. With one entry per physical page of the system. With one entry per physical page of the system. Okay. So this paired array in memory entry is per physical page rather than per process, I assume. Okay. Thus, when a page is accessed, the time field would be set by hardware. When a page is accessed, the time field would be set by hardware to the current time. Okay, then when replacing a page, the operating system could simply scan all the time field in the system to find the least recently used page. Okay. Unfortunately, as the number of pages in the system grow, scanning a huge array of time just to find the absolute least recently used page is prohibitively expensive. Imagine a modern machine with 4 GB of memory chopped into 4 KB page. This machine has 1 million pages, and thus finding the least recently used page will take a long time, even at modern CPU speeds. Which begs the question, do we really need to find the absolute oldest page to replace? Interesting. Do we really need to find the absolute oldest page to replace? Can we instead survive with an approximation? Now, the follow-up question is that what kind of approximation we need here? Can we instead survive with an approximation? Okay, and then the new crux of the problem, how to implement an least recently used replacement policy, given that it will be expensive to implement perfect least recently used. Can we approximate it in some way and still obtain the desired behavior? Yeah, what approximation here that we will do? Okay, approximating least recently used. Oh, that's also considering the debates. Okay, let's continue. As it turns out, the answer is yes. Okay, approximating least recently used is more visible from a computational overhead standpoint, and indeed, it is what many modern systems do. The idea requires some hardware support in the form of a use bit, sometimes called the reference bit. The idea requires some hardware support in the form of a use bit. Okay, sometimes called the reference bit, the first of which was implemented in the first system with patching, the Atlas one level store. Okay, yeah, I think what is it called? I think the book mentioned this use or reference bit in previous chapter, probably around patching introduction here, maybe. Okay, yeah, I think it was when we talking about the page table entry. What is in the page table entry? What kind of information we store in the page table entry? If I remember correctly, okay, there is one use bit per page of the system, and the use bit live in memory somewhere. They could be in the per process page table, for example, or just in an array somewhere. Whenever a page is referenced, that is read or written, the use bit is set by hardware to 1. The hardware never clears the bit, though, that is set it to 0, right? So once the hardware set it to 1, I assume it will be 1, or it will never be 0 again. Maybe that's what it means. The hardware never clears the bits. That is the responsibility of the operating system. Oh, okay. So the one setting the use bit is the hardware, but the one who clears that up or set it to 0 is the operating system. Interesting. There's what is it called? The separation, I guess. What the hardware do and what the operating system do. Okay. How does the operating system employ the use bit to approximate necessary use? Okay. Does the operating system employ the use bit to approximate necessary use? Well, there could be a lot of ways, right? But with the clock algorithm, one simple approach was suggested. Imagine all the bits of the system arranged in a circular list. Imagine all the bits the system arranged in a circular list. A clock hand points to some particular page to begin with. It doesn't really matter which. Okay. When a replacement must occur, the operating system checks if the currently pointed to page P has a use bit of 1 or 2. When a replacement must occur, the operating system checks if the currently pointed to page P, the currently pointed page, I guess, has a use bit of 1 or 0. If 1, this implies that page P, the currently pointed page, right, was recently used and thus is not a good candidate for replacement. Thus, the use bit for P is set to 0. That is clear. It's not a good candidate for replacement. Okay. It is not a good candidate for replacement, but we clear the use bit and the clock hand is increment to the next page. Okay, P plus 1, right? The algorithm continues until it finds a use bit that is set to 0. Implying this page has not been recently used. Or in the worst case, that all pages have been, and that we have now searched through the entire set of pages, clearing all the bits. Right. I mean, again, this is the worst case, I guess. If all the pages have the use bit of 1, and then suddenly we are going back to the page P, which is clear previously, are we just gonna free up page P? Maybe. I mean, it is the worst case, right? All the pages have been accessed recently, so the use bit is 1 instead of 0. Like, imagine the all pages have the use bit of 1 here. So maybe something like this. This is page P, then page P plus 1, plus 2, and so on. Use bit 1, and then we maybe something like this. We change that to use bit 0, right? This one is also the same. 1 use bit 0. I mean something like this. Use bit 1, use bit 0, and this is also the same. Like everything have the use bit 1, right? And then we clear that out, and then we are going back to PHP again, which has use speed 0 from this process. Yeah, maybe something like that. All the pads have been recently used. All the pads have been recently used, and that we have now searched through the entire set of pads, clearing all the pads. Okay, note that this approach is not the only way to employ a use speed to approximate least recently used. Indeed, any approach which periodically clears the use speed and then differentiate between which pads have use speeds of 1 versus 0 to decide which to replace would be fine. Again, any approach which periodically clears the use speed and then differentiate between which pads have use speeds of 1 versus 0 to decide which to replace would be fine. The clock algorithm of Gorbatos was just one early approach, which met with some success and had the nice property of not repeated and had the nice property of not repeatedly scanning through all of memory looking for an unused page. Okay. Oh, there is the 8020 workload with clock. Interesting. But wait a minute. Why is it suddenly different than the 8020 here? Oh no, guess it's kind of the same. I mistake that with the looping workload here. My bad. The behavior of a clock algorithm variant is shown in figure 22.9. This variant randomly scans pages when doing a replacement. When it encounters a page with a reference bit set to 1, it clears the bit that is set it to 0, right? Set the use bit or reference bit to 0. When it finds a page with the reference bit set to 0, it chooses it as its victim. Okay. Yeah, the algorithm chooses it as the page to replace. As you can see, although it doesn't do quite as perfect least recently used, it does better than approach that don't consider history at all. Right, this, what is it called? There's some difference here between the least recently used and the approximation of least recently used. Okay. Considering 30 pages. Okay. I guess let's continue this on the next session. Right, oh, there's also tracing here and then summary. Okay, yeah, let's continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.